Jai Hind, welcome to the course Network Analysis and Synthesis, and we are going to discuss about the transient behavior of this course. The learning objectives of this topic is transient behavior of first and second order systems. So, for first order and second order system, I have taken RL circuit as a first order system and RLC circuit as a second order system, and these circuits are subjected to step input, impulse input and sinusoidal input. So, basically I am going to discuss about the transient behavior of RC and RLC circuit when they are excited by step input, impulse input and sinusoidal input. What do we mean by the transient behavior? Basically it is the part of your time response. Time response consists of two parts. One is the transient response and other one in the steady state, and both together known as the time response of the circuit system or network. So, by transient response we mean the manner in which response goes from initial state to the final state, and this transient response exists between two steady states. When the circuit is opened for a very long time, that is one steady state, and other one when the circuit is closed for a very long time. So, in between these two steady states, the transient states prevails, and the causes of the reasons for occurrence of transient phenomena is due to when the circuit is suddenly closed, connected or disconnected to or from the supply, then the transient phenomena occurs, or when there is sudden change in the applied voltage from one finite value to another finite value, then also the transient behavior occurs, or when the circuit is short circuited. So, these are the conditions when the transient phenomena occurs in a circuit. So, the transient currents are not caused by any part of the supply. So, this is not the part of the supply, but they are entirely associated with the change in the stored energy in the capacitors or inductor, whatever the storing elements present in the circuit. If it is a RL circuit, then we have the inductor as a storing element. If it is RLC circuit, then the inductor and capacitors, they are the storing elements. They store energy in the electric and magnetic field. So, I am going to discuss the transient analysis for say series RL circuit and series RL circuit. So, first I will take the RL circuit, and the input is the step input. So, this is the basic circuit diagram of a series RL circuit. Here the step input is Vt. So, Vt is defined as Vt is 0 for t greater than t less than or equal to 0, the Vt is 0. So, this is basically this is Vt is nothing but it is like this. This is Vut, where Ut is 1 for t greater than or equal to 0 and 0 for t less than 0. So, this is the step voltage of value V. So, when the switch is closed, so we just apply the Kirchhoff's voltage law to write the dynamics of this RL circuit, and it is like this. This is RIT plus LDI upon dt equal to VUT. So, this is the input. This value is V when t is greater than or equal to 0, its value is 0 when t is less than 0. So, this is the when the t is closed, when the switch is closed at t is equal to 0. Now, take the Laplace transform. So, basically it is a differential equation. To solve a differential equation, we have to apply the Laplace transform. So, take the Laplace transform of this of the above equation, we get this expression we get, and find the expression for Is. So, we get Is. So, this is the expression for Is. So, there are two components we can see here. So, this is due to input, and this is due to initial condition. So, just carry out the partial fraction expansion of this equation. Carry out the partial fraction expansion. You are very much familiar with this partial fraction expansion. To get the inverse Laplace transform. So, this is the partial. So, this is the partial fraction expansion. So, if we take the inverse Laplace transform, so we have this expression, this one plus this one. So, this is called forced response. If you remember, in the last class we discussed the what is free response and what is the forced response. So, this is forced response and this is the free response, or you can say the natural response. When the response is due to the initial conditions, we get the free response, and when the response is due to the input, we get the forced response. And in the given circuit, the initial current through the inductor is 0. So, this I0 is 0. If we put there, we get this expression. V by R 1 minus e to the minus R by L into T. So, transient part of this, how will get it? So, the total response, time response is ITR plus ISS. ITR means transient response. If it is current, then it is the transient current. This is the steady state current, and the transient current is ITR is nothing but we just subtract the steady state part of the current, we get the transient. So, there here it is written IT minus IS. ISS means steady state. This is ISS, we can say steady state. So, it is coming this much, minus V upon R e to the minus R by L into T. If you go to plot the complete response of this RL circuit, say this is your time axis and this is your IT. Okay, look at here, when t is 0, so this term is e to the minus t0, so it is e to the power 0, so e to the power 0 is 1. So, this is 1 and 1 minus 1 is, so it is 0. So, at t is equal to 0, the total time response or total current of the RL circuit is 0. And take the other extreme cases when t is infinite. So, when t is infinite, so it is e to the minus infinite, so 1 by e to the infinite, so it is 0. So, this is the value we can say, this is ISS, which is nothing but V upon R. So, this is the V upon R, this is the steady state, and just go for the different time. Here we have the another term from the current t is equal to tau is L upon R. L upon R is nothing but is the time constant of a RL circuit, and for one time constant, then we have the 2 tau. Similarly, we have the 3 tau and so on. So, for when t is equal to tau or tau is L upon R, so this is V by R 1 minus e to the power minus 1. So, it is coming 0.63 into V by R, And what is V by R? V by R is the steady state value of this current. So, for one time constant the value of current will rise, say this is suppose 0.63 V by R. So, if you go, it will be like current will go like this, it will be like this. So, this is the behavior of the RL circuit. This is the current response in RL, and for the transient we can draw this part of the, for the different value of time we can plot the transient behavior of the circuit. Similar analysis can be if the input is your impulse. So, in place of the ut it is delta t, switch is closed, write the Kirchhoff's voltage law, we get this differential equation. To solve this differential equation we take the Laplace transform, and we also see that the initial current through the inductor is 0. So, this is the, and when we take the Laplace transform we get this expression. So, Laplace transform of delta t is 1, so it is V, whereas in the previous case it was 1 by S. Laplace transform of unit step is 1 by S, so it is V by S. Here the Laplace transform of delta t is 1, so it is simply V. So, write the expression for Is, this is V by L S plus R by L. So, take the inverse, so it is in the standard format. So, directly we can write the expression for it in the time domain, and we can plot. So, here we also plot the wave shape. So, when t is 0, so its value is V by L. So, say this is V by L, this is 0. Okay. When t is infinite, so its infinite means e to power minus infinites. So, basically when t is equal to infinity, so it is I infinity is nothing but V by L e to power minus R by L into, if it multiplies, so it is V by L, then e to power minus infinity. So, V by L 1 by e to power infinity. So, its value is 0. So, when t tends to infinity, the response will just will be like this, and it is asymptotic along the time axis, and at t is equal to infinity its value is 0. So, it is, so it will start from V by L, and for we can have the 1 time constant, 2 time constant, 3 time constant, and so on, 1 tau, 2 tau, 3 tau, and so on. So, this way we can plot the time response of RL circuit. So, this is the response of the current when input is impulse, whereas in the previous case the input was step, here the input is impulse. Now, we take the another input, that is the sinusoidal. So, the expression for Vt is V sin omega t. So, in place of Vt we write the V sin omega t, write the expression and take the Laplace transform. So, Laplace transform of this sin omega t will be this one. Okay, and we also have seen that the current through the inductor is 0. So, initial current is 0. So, write the expression for Is. So, for Is, this is the expression for Is. So, there is a pole at S is equal to minus RL, and there is a complex conjugate pole. So, this one. So, take the partial fraction expansion here. So this is v omega by L. This is the this one, this is other one, and this is the for the S is equal to minus R by L pole. So this A3 is the pole residual at S is equal to minus RL, and A1 and A2 are the pole residuals for S is equal to j omega and S is equal to minus j omega, because they are the conjugate poles. So if you take the value of find the value of A1, the value of A2 will be the just complex conjugate. So no need to go for the A2. If you find the A1, you can write the directly the expression for the A2. So this way, by carrying out the partial fraction Heaviside expansion theorem, we can find the value of A1, which is coming this much, and the A2 this much. So we can see here, this is the complex conjugate. So this, and similarly we can get the coefficient A3. So using the Heaviside expansion theorem, we can find the A1, A2 and A3 for the coefficients in the above equations. Now put these coefficients in the equations, we get this one. Now taking the inverse Laplace transform, so we are getting this expression. So this is the expression for IT in time domain. So what, just we go for the simplifications. So let this is the R plus j omega is z, it was j theta, and R minus j omega is L is, say this, it was minus j theta. So for simplifications, I have assumed R plus j omega L is equal to, so this is in the rectangular form, this is in the polar form. So we can putting all this, so on simplifications we get this. This is the finally value of the current, B by Z sin omega t minus theta plus B omega L by Z square, this one. So this is the final expression for current in RL circuit when the circuit is excited by a sinusoidal input. So we can see that the current lags behind the voltage by an angle this much, tan inverse omega L by R. If the resistance is 0, then theta is 0. So it will be the perfectly in case of the perfect inductor, the R is 0, so it will be lag by the 90 degree. So these are the transient behavior of RL circuit when the inputs are step input, impulse input and the sinusoidal input. Now come to the second order system. So for the second order system, I have considered the series RL circuit, and it is excited by a step input. So just write the Kirchhoff's voltage law for this circuit. So RIT L di upon dt 1 by C IT into dt V ut. Take the Laplace transform. So this is the first order variable. So SLIS, and initial current through the inductor and the initial voltage across the capacitor, they are 0. So all the initial conditions are set to 0. In this equations, the initial conditions are set to 0. So initial conditions are set to 0. So write the expression for IS. So this is V by L S square R by L S plus 1 by LC. So take the roots of the denominator equate to 0 just to find the roots. So roots are S1 is this much and S2 is, so there are 2 roots. Now let omega 0 is equal to 1 by root LC. If you remember you can say the transfer function of a second order system will come in this form, omega n square S square plus 2 zeta omega n S plus omega n square. This is the general form of a second order system. So let omega 0 is 1 by root LC and zeta omega 0 is R by 2L. So we get the value of this zeta, that is the damping ratio is R by 2 root over C by L in case of the series RL circuit. RLC circuit, we get the zeta R by 2 root over C by L. Now, so S1 is putting the value of zeta and putting the value of, or writing the S1 and S2 in terms of omega 0 and zeta. So we get the S1 is equal to minus zeta omega 0 plus omega 0 root over zeta square minus 1. And similarly, we can write the S2, which is minus zeta omega 0 minus omega 0 root over zeta square minus 1. So this is the expression for IS. So we can find the coefficient A and B just using the Heaviside expansion theorem. So A is coming this much. Similarly, we can get the coefficient V, or we can say the pole residuals at S is equal to S2. So this is the value of B. So B is this much. So putting this value of A and B, we get the IS. So this is the IS, then take the inverse Laplace transform, we get this IT. Now here we can put the value of S1 and S2, so we get this. So these are the expression for IT in time domain. So this is the expression for S1 and this is S2. So these are the expression for current IT when the input is step input. So depending upon the values of R, L and C, there are three cases. So R by 2L, when the R by 2L is greater than this 1 by root LC, this is the case of damped condition, over damped condition, or we can also define in terms of zeta, R by 2 root over C by L. Okay. So in this case zeta is greater than 1. If the damping ratio is greater than 1, the case is the underdamped. When the R by 2L is the less than 1 by root LC, so it is the case of the underdamped condition. So that is, in this case, the zeta is less than 1, and R by 2L is equal to 1 by root LC, so it is critically damped. So here zeta is 1. So if you go to plot the different damped cases, over damped, under damped and critical damped, we get like this. So this is the topmost, this is the case of the under damped conditions. Here the zeta is less than 1. This is the critically damped, the zeta is 1, and in the bottom one here the zeta is greater than 1. So these are the three cases, over damped, under damped and critically damped, when the RLC circuit is subjected to a step input. So similar analysis can be carried out by applying the sinusoidal input or any other input. I have discussed here the one RL circuit and RLC. We can also discuss the RC circuit. So in place of, suppose this is your input, this is your VUT and this is your switch. This is your C, this is your R, and this is switch is closed at t is equal to 0. So this is your IT. So we can write the expression for VUT VUT is equal to RIT plus 1 by C 0 to T IT TT. We can write. Okay. So this is take the Laplace transform. Take the Laplace transform and equate initial conditions to 0. Conditions to 0. So V by S. So it is RIS plus IS upon SC, because the charge, initial charge across the capacitor is 0. So, and we can find the value IS. So IS is V by S R plus 1 by SC. Okay. So R plus 1 by SC here. One step we can write here. So IS R plus 1 by SC. Yeah. I am writing here R plus 1 by SC. Okay. Now we can carry out the partial fraction expansion, find the value of the constant, take the inverse Laplace transform and get the similar expressions as we got in case of the RL circuit. So this way we can carry out the transient behavior of any circuit, whether it is RL circuit or RC circuit or RL series circuit or RL parallel circuit. Here I just discussed two cases with different inputs, that is the RL and RLC, just discussing the first and second order system. So thank you very much. We just take the other one of this unit, that will be the interconnections of two port networks, in the next class. Thank you very much. Jai Hind.